Welcome back to my channel. Today we are looking at problem 10.73. A sphere of radius r0 is equal to 20 centimeters and a mass m of 1.2 kilograms starts from rest and rolls without slipping down a 40-degree inclined plane that is 15 meters long. First, it's asking us to calculate its translational speed when it reaches the bottom. To find the translational speed at the bottom, it is a energy equation. We have to use conservation of energy. Conservation of energy from purely gravitational potential energy to both translational and rotational kinetic energy at the final position. So, if we drew our ramp, and it is approximately 15 meters long, 15 meters long being that way. It is a ball or sphere with a radius 0.2 meters and a mass of 1.2 kilograms. Up here at the top of the incline, there's only potential energy. But down here, at its final position, it will have both rotational and translational kinetic energies. So, to calculate the translational kinetic velocity at the end of the incline, conservation of energy, so it goes from potential energy to kinetic energy, translational kinetic energy to rotational, where I is the moment of inertia. The moment of inertia is 2 over 5 mr squared. And where angular velocity is equal to tangential velocity over the radius. Plugging these two values in, you would get mg delta h equals 1/2 mv squared plus 1/2 2 over 5ths mr squared times v squared over r squared. Now, your terms, they cancel out. Your r squareds cancel out. Your masses will cancel out throughout the entire equation. And your 2's here also cancel out. So you should be left with something like g delta h equals 1/2 v squared plus 1 over 5th v squared. To find the height, assuming that this is delta h is equal to L sine theta, where theta is that, and this is L. Getting all this in, your velocity is 11.62 meters per second. To calculate the rotational speed when it reaches the bottom, you would just use the relationship angular velocity is tangential velocity divided by the radius. You know what the tangential velocity is. That's 11.62 meters per second over radius, which is just 0.2 meters. This will yield you 58.12 radians per second. So this would be the angular velocity it would have at the bottom of the incline. To find the ratio between translational and rotational kinetic energy at the bottom, it's purely just translational kinetic energy divided by rotational kinetic energy. So plugging in your formulas, you have 1/2 mv squared divided by 1/2 2/5 mr squared times v squared over r squared. Here, your r squared terms will cancel out, your v squared terms will cancel out, and your mass term, your m term, will cancel out. Your 2 term will also cancel out here, so your final answer would just be 1/2 over 1/5, which is 2.5. In part A, the answer is not dependent on the radius of the sphere. The radius of the sphere cancels out here, so it does not have an impact on the equation. It also doesn't depend on the mass, since the masses also cancel out here, here, and here. So these all go away. And the main things that would contribute to it would be height and velocity. For rotational speed, radius does impact it, but mass does not have an impact on the answer. Only radius does, the radius of the sphere. And for part C, neither mass nor rotational or tangential velocity impact the final equation, the final answer, since your mass terms cancel out here, your radius terms cancel out here, and your velocity terms cancel out there.